Let's see if we can explain these right-hand rules and induced currents and the magnetic fields that induce currents and the magnetic fields caused by induced currents. We'll try one more time and we'll take it in a few steps, right? I got a little prop this time, right? Pretend this is our loop of current, right? Maybe it's like this, right? You got a battery and a resistor around. There's a switch so we can turn the current on and off, right? That's important, being able to turn the current on and off. So, while there is a current flowing through this, right? In this image, the current flows this way, right? Clockwise, round and round. And so if it flows clockwise around and around, right? This top piece has a current flowing this way. I stick my thumb in that direction. It points towards you outside the circuit, but inside everywhere it points into the middle. So my magnetic field is going inward while my loop is active, right? While there is an active current, I have a magnetic field, and it will be a constant magnetic field, right? Because the current will be constant. Because it's ideal current, right? Ideal circuit. And so as it's constant, there's no induced current. Constant, no induced, right? We need change to induce a current, right? For self-induction. Because if I have my loop, right? And it's currently active, it's going round and round, and then I open this up, right? I open this up. In an ideal world with all this magic, we're forgetting about real life and blah, blah, blah. The current just stops. Boop, gone, right? But in reality, it takes time for that current to be turned off. Now, that time could be really small, like microseconds and even smaller, but it still takes time, right? And so I have a current flowing around, and it's creating a magnetic field going into my loop, right? Remember that. There currently is a magnetic field going in, and then I flip the switch and turn it off. And so now there's not. But there's a moment where the magnetic field goes from maximum to nothing. It goes really fast. But during that time, it's actively changing, right? And there used to be a lot of magnetic field going in, and now there's not any. And so while it's changing, it's resisting that change. And so it's going to induce a current in itself to fight that change. And it had a lot of magnetic field going inside, right? And now it doesn't. So it wants to make more magnetic field going in, right? It wants to make more going in. And so I stick my thumb in the direction that I want the magnetic field to point and curl my fingers in the direction of the magnetic field. Curl it in the direction of the current, right? Magnetic field is my thumb. The curling fingers is the current, and it will induce a current in itself in a clockwise manner. Similarly, if it's off, if there's no current at all, if the switch is open, and I close the switch, before there was no magnetic field going in my loop. And afterward, there was a lot of magnetic field going in my loop. And it doesn't like that change either. It doesn't care whether there's a lot of magnetic field or no magnetic field. It just doesn't want it to change. That's the key, right? And so if there was no field and then there suddenly was field going in this way, well, it doesn't like that change. And so it's going to try to fight it by making a field go out the other way, out towards you, right? And so I stick my thumb in the direction of that field and curl my fingers. And when I first open the switch, it will induce a current, a rather large current at times, counterclockwise. And you may have electricity flowing backward in a circuit when you first turn it on. Then while it's on, it's just fine, right? It's constant, no big deal. And when you turn it off, suddenly there's a huge current because there's a massive change. Sometimes, now most of the time, this induced current is small, right? But not always. It can be rather large, especially when you're flipping switches. That's why that electricity arcs across switches. You see the bright flashes and stuff like that, because it's a really, really sudden change in the magnetic field. And so that can induce a current many times bigger than the natural current that was flowing through my circuit, right? But remember, it's trying to fight the change, right? If there was current flowing in and that current's being lessened, it tries to make more. If there was no current and suddenly is some added, well, it fights that by pushing back. It's resisting the change, right? And there doesn't even have to be a magnetic field in that moment, right? It's a pretty common idea that, especially for alternating current, right? It's what we use everywhere, alternating current. That current starts positive, goes negative, goes positive, goes negative, positive, negative, positive, negative, alternates in a sinusoidal pattern. Well, while it's all positive, it's changing down to negative. It's lessening, lessening, and lessening, right? Until it reaches the bottom, and then it levels out, and then it starts going positive and increasing and increasing. There is a point in the middle, right? Where there's no magnetic field at all. But that's also the point where there's the most amount of change, right? That's where change is maximum. And so you get a maximum amount of induced current when there's zero magnetic field going through your loop. Because again, it doesn't matter about how much magnetic field there is. What matters is how much it's changing. That's the key, change.